Hi everyone, in this video and in this chapter we're going to be learning about probability. Previously we've learned about summarizing data, we've spent some time with that, and now we're getting into probability because it's a big part of inferential statistics. So we can think about the probability of an outcome as the likelihood of observing that outcome. So we're going to begin with probability rules. First, let's understand random processes and the law of large numbers. So first, the word random suggests an unpredictable result or outcome. A simulation is a technique used to recreate a random event. So simulations can be either tactile or virtual. Tactile meaning we can do something physical like flipping a coin, or virtual we would use like a computer to pretend that it is flipping the coin. In both instances, the goal of the simulation is to measure how often a certain outcome is observed. In this case, it would be maybe to say how many times do we get heads when we flip the coin. So let's take a look. To see this idea, let's suppose we flip a coin 100 times. And we're going to compute the proportion of heads observed after each time we flip the coin. So if, let's say, the first flip we get tails, our proportion would be 0 because 0 heads out of 1 flip. Let's say the second flip is heads, so we have 1 heads out of 2 flips, which is a proportion of 0.5 or 50%. Let's say the third flip was heads. The proportion would be 2 heads out of 3 flips, or about 66.7%. So here's actually the proportion of heads versus the number of flips on these graphs, and then we just repeat the experiment for the second graph. So same experiment, flipping the coin 100 times, just done twice. So just taking a look at what's happening here, if you notice the points plotted for each proportion, basically there's a point corresponding to each flip. As we get toward the 100th flip, this proportion is getting very close to 50%. Same thing with when the experiment was repeated. So the graphs that we just saw illustrate a random process. So a random process represents scenarios where the outcome of any particular trial of an experiment is unknown, but the proportion, or you could say that it's the relative frequency, of a particular outcome is observed, and it approaches a specific value as the number of trials increases. So for us, it was 50% of the time we got heads, and we would think that that would make sense if there's two options. 50% of the time we should get heads, 50% of the time we should get tails. Now, probability, which we're talking about in this chapter, is a measure of the likelihood of a random phenomenon or chance behavior occurring. Probability deals with experiments that yield random short-term results or outcomes yet reveal long-term predictability. So the long-term proportion in which a certain outcome is observed is the probability of that outcome. So for our coin flipping, the probability of getting heads is about 50%. Now let's talk about the law of large numbers. As the number of repetitions of a probability experiment increases, so basically the more times we repeat the experiment, the proportion with which a certain outcome is observed gets closer to the probability of that outcome. So if you think back on our coin flipping, the chart didn't look quite like it was approaching 0.05, 50%, until we kept repeating. So as we got closer to 100 flips, that's when it was getting closer to the probability of that outcome of heads being 50%. So the law of large numbers is often interpreted as a non-existent law called the law of averages by folks who misunderstand the law of large numbers. So you probably heard people talk about the law of averages. In probability, an experiment is any process with uncertain results that can be repeated. So the sample space of an experiment, S, of a probability experiment, is the collection of all possible outcomes. So for our coin flipping, that would be either heads or tails. An event is any collection of outcomes from our probability experiment. So an event may consist of one outcome or more than one outcome. We denote events with one outcome, sometimes called simple events, with E, so E sub I. And in general, Events are denoted using capital letters such as capital E. Okay, let's take a look at this example. A probability experiment consists of rolling a single fair die. That just means that there's nothing wrong with the die to make it land a certain way. First, let's identify the outcomes of the probability experiment. Okay, there's 6 sides to this die, so 6 options. So each event, and because there's 6 of them, we denote them E sub 1 through 6. So we're going to say rolling a 1 is denoted 2 ways, E sub 1, or you can use a set squiggly braces like this with a 1 in the middle, and you can do that for each of the possible outcomes. Now we determine the sample space. The set of all possible outcomes forms a sample space. So S, capital S, is the possible outcome of 1, 2, 3, 4, 5, or 6. And there are 6 outcomes in the sample space. Okay, let's now define the event E, which we're going to decide to be a roll of an even number. So that's our event. So E equals the roll of an even number, which is the set containing 2, 4, and 6, because those are the even numbers on a die. So a fair die, we've mentioned this, but it's one that has equal possibilities for each of the outcomes. So 2 is just as likely as rolling a 5. A die is considered loaded if a certain outcome is more likely than others. All right, now let's apply the rules of probabilities. So the first one, the probability of an event, E, is denoted like this. So when you see P, you can read this of E. This is saying the probability of the event E. It must be greater than or equal to 0 and less than or equal to 1. And pretty much, if you think of those as percents, your probability of something happening, it has to be 0% or more likely to happen, and it can't be more than 100% likely to happen. And then number 2, the sum of the probabilities of all outcomes must equal 1. So if we had, let's say, n events in our sample space, the probability of event 1 plus the probability of event 2 and so on, up until the last probability of the last event, the total has to be 1. If you think of our coin flipping, the probability of heads is 50%, the probability of flipping tails is 50%, so total is 100%, or 1. Now, a probability model lists the possible outcomes of a probability experiment and each outcome's probability. A probability model must satisfy both the rules we just talked about. So let's take a look at this example. The color of a plain M&M milk chocolate candy can be brown, yellow, red, blue, orange, or green. Suppose a candy is randomly selected from the bag. Here's a table that shows each color and the probability of drawing that color. And so when you randomly select, you're not really looking what you're grabbing until after you've grabbed it. So to verify that this is a probability model, we must show that rules 1 and 2 are satisfied. So each probability is greater than or equal to 0 and less than or equal to 1. Probabilities are here. So rule number 1 was satisfied. And then if we add up all the probabilities from each outcome, we do get 1. So rule 2 is also satisfied. So what we say here is this table is a probability model. If an event is impossible, the probability of the event is 0. It's like saying 0% chance of it happening. If an event is a certainty, the probability of the event is 1. You can say 100% chance that it's going to happen. And an unusual event is one that has a low probability of occurring. So anything with low probability, we can call that an unusual event. It could still happen, but it has a low probability of happening. All right, next, let's compute and interpret probabilities using the empirical method. So for this method, we say that the probability of an event, E, is approximately the number of times the event is observed, and then we divide that by the number of repetitions of the experiment. So pretty much, this is saying that the probability of an event is approximately equal to the relative frequency of that event. And remember the relative frequency, this is going to be the frequency of our event E divided by the total or number of trials of the experiment. So let's take a look at this example. An insurance agent currently insures 182 teenage drivers, ages 16 to 19. Last year, 24 of them had to file a claim on their auto policy. Based on these results, the probability that a teenager will file a claim on his or her auto policy in a given year is 24 out of the 182, which is about 13.2%. So for every 100 insured teenage drivers, we expect about 13 to have a claim on their auto policy based on this probability. The data in this table represents the results of a survey in which 200 people were asked their means to travel to work. Okay, so let's take a look real quick. We have drive alone, carpool, public transportation, walk, other means, or work at home, and then the frequencies. So we're going to use the survey data to build a probability model for means of travel to work. And remember, we talked about what needs to be listed in a probability model. It's the outcomes and each outcome's probability. Then we're going to estimate the probability that a randomly selected individual carpools to work, so one of the means of travel. And then we're going to interpret this result. And then, would it be unusual to randomly select an individual who walks to work? So first, if we add up the frequencies, we get 200 individuals in the survey. The individuals can be thought of as trials of the probability experiment. The relative frequency for drive alone would be the 153 from our frequency out of the total number of people, which was 200, so 0.765. And we do this for each of the other means of travel, and we get the probability of each of the means. Now, from our table, we can estimate the probability to be 11% that a randomly selected individual carpools to work, because 0.11 is 11 out of 100. We can say if we were to survey 100 individuals, we would expect about 11 of them to carpool to work. And then the probability that an individual walks to work is approximately 0.025. So if you make this a percent, notice that's going to be 2.5%. So that means if we survey 1,000 individuals, we would expect 25 to walk to work. And therefore, it is unusual because it has a very low probability for someone to walk to work if we randomly choose them. Next, let's compute and interpret probabilities using the classical method. So we just did the empirical method, now the classical method. And so this is a method of computing that requires equally likely outcomes. And its experiment is said to have equally likely outcomes when each simple event has the same probability of occurring. So computing using the classical method, if an experiment has n equally likely outcomes, and if the number of ways that an event E can occur is just denoted with the letter m, then the probability of the event, which remember we denote that as P of E, so the probability of the event is the number of ways the event can occur, which we're using m to represent that, divided by the number of possible outcomes, which we're using n to represent that. So it's just m divided by n. So if our sample space is S for this experiment, we can say that our probability of our event is n of our event over n of our sample space, where n of our event is just the number of outcomes in our event, and n of our sample space is the number of outcomes in the sample space. So number of outcomes in our event divided by the number of outcomes in our sample space gives us the probability of our event using this classical method. So let's try this out. A pair of fair dice is rolled. Fair die are die where each side is equally likely to occur. So compute the probability of rolling a 7. Compute the probability of rolling snake eyes, which is just 1 and 1. And then comment on the likelihood of rolling 7 versus rolling 2, or 1 and 1. Okay, so there's 36 equally likely outcomes in the sample space, and you can see them here because if we have 2 die, this is all the possible outcomes. So our sample space has size 36. Here's what we're actually questioning. Rolling 2, which is snake eyes, and then rolling 7, which occurs a few different ways. It's actually highlighted in red. So 7 can be done with a 6 and 1, a 5 and a 2, 4 and a 3, and so on. So notice the number of our outcomes in our sample space was 36, and our first event was to roll a 7. And so the ways we do that is the first die is a 1, the second die is a 6. Notice that this is different from, or the first die being a 6, and the second die being a 1. And then similarly with 2 and 5 and 3 and 4. So there's 6 outcomes for our event, so the number of outcomes of our event is 6. And using our formula to compute the probability using the classical method, our probability of our event of rolling a 7 is just 6 divided by 36, or the number of outcomes of our event, over the number of outcomes in our sample space, and then we simplify and get that the probability is 1/6 of rolling a 7. So now, the second event, let's rename it a different letter. We're going to say the event F is the event where we roll a 2, which can only be done with a 1 and a 1. There's only one way to do it, and so it has one outcome. So the number of outcomes in our event F of rolling 2 is just the number 1. And so our probability of rolling a 2 is 1 over our 36 outcomes in our sample space. So the probability is 1/36. Much smaller probability than rolling 7. So since the probability of rolling a 7 was 6 out of 36, and the probability of rolling a 2 was 1 out of 36, rolling a 7 is actually 6 times more likely than rolling a 2. And you could just say that because if the denominators are the same, we would just multiply this 1 by 6 to get this 6 right here. In other words, in 36 rolls of the dice, we expect to observe about 6 outcomes where we get 7, and then only 1 time will we get 2. Now let's take a look at this example. Sophia has 3 tickets to a concert, but 4 of her friends actually want to go: Yolanda, Michael, Kevin, and Marissa. So to be fair, Sophia randomly selects 2 people who can go with her. Let's first determine the sample space of the experiment. So what that basically means is we're going to have to list the possible simple random samples of size 2, because she can only take 2 other people because the 3rd ticket is for her. Then compute the probability of the event that Michael and Kevin attend the concert. Then we're going to compute the probability of the event that Marissa attends the concert, and then interpret our probability from Marissa attending the concert. So here's our sample space. Now, one of the ways you can do this is kind of focus on one person out of the pair at a time. So let's say we said Yolanda, we compare her with Michael, Marissa, and then Kevin, and then that's all the combinations with her. Then we can move on to Michael and say Michael with Marissa, and then next will be Michael with Kevin because it was already him with Yolanda. And then the only other outcome we haven't accounted for yet was Kevin with Marissa. And so there's 6 possible outcomes. And so to answer the probability of Michael and Kevin attending the concert, that only occurs once. So it's 1 out of 6 probability, 1/6 probability that Michael and Kevin both attend the concert. And then to answer Marissa attends the concert, that probability, out of our 6 outcomes, 3 of them had Marissa in it. So 3 out of the 6 is 50%. So to interpret that, we can say if we conducted this experiment 1,000 times, about 500 of the experiments would result in Marissa attending the concert. Similarly, we could say if we did it 100 times, 50 of them, Marissa would attend the concert. And actually, for any of the friends, if you just focus on one of them, it would be about 50% for each one. Okay, let's take a look at this one. We're going to use the empirical method here and the classical method. So suppose that a survey asked 500 families with 3 children to disclose the gender of their children, and the survey found that 180 of the families had 2 boys and 1 girl. So let's first estimate the probability of having 2 boys and 1 girl using the empirical method. Then we're going to compute and interpret the probability of having 2 boys and 1 girl using the classical method. And remember, for the classical method, the outcomes have to be equally likely. So we're just going to assume that boys and girls are equally likely to be born. So A, the empirical probability of our event, which our event is 2 boys and 1 girl. Remember that this is just approximately equal to the relative frequency. So from the survey, we know that 180 out of the 500 had 2 boys and 1 girl. So then our probability is about 36%. Now, for the classical method, we have to do a little bit more to figure this out. What we're going to do is first figure out the sample space by constructing a tree diagram of our equally likely outcomes. So we're going to start by taking the first child and drawing 2 branches off. First child could be boy or girl. And then from there, for the second child, if it was boy, the first one was boy, the second one could be boy or girl. So 2 branches off of that. Or if it was girl, 2 branches off of that. So basically from the second child, we drew 4 branches. And then we do something very similar for the third child. And so we have all of our possible outcomes listed over here. Now to find the sample space S, we're going to look at the ends of all of our branches basically and list how many outcomes there were. There was 8 total. And then just B is boy, G is girl, and these were the 8 outcomes. So for our event of 2 boys and a girl, it occurred 3 times. So it was first child was boy, then girl. The next one was first child was boy, then girl, then boy. And the last one was first child was girl, and then boy. So 3 out of this 8 possible outcomes gives us a probability of 37.5%. So the probability of a family with 3 children having 2 boys and 1 girl is 0.375. So if we repeat this experiment 1,000 times, just assuming that the outcomes are equally likely, we could expect 375 of the trials to result in 2 boys and 1 girl. So this was using the classical method to compute this probability. The last thing we're going to do is just recognize and interpret subjective probabilities. So a subjective probability is an outcome is a probability obtained on basis of a personal judgment. So for example, an economist predicting that there is a 20% chance of a recession next year would be a subjective probability. That's because we can't have an experiment where we have all the same factors, everything to be repeated to figure this out, an actual numerical value for our probability, where we have our relative frequencies involved. But what we can use is like data. So the economist might have used past data to come up with this educated guess. So pretty much a subjective probability is more so, think of it like an educated guess, rather than something that we've computed with relative frequencies. All right, that's it for this one. Thanks for watching.